And so I'll go over some questions that you will find on your exam. So let's start with this table. This is gold if you have trouble with your kinematic equations, and I put them in a very deliberate order here. I've made two columns, variables included and variables not included. So in a question stem, you'll be given all but one of any of these included variables. And so when you're hunting for one, pick the equation corresponding to what you need. So if you have the final velocity and initial velocity of acceleration, you just need to find distance. That's the equation you're using. And so when you have these in your notes, it's a lot easier to just instantly think, oh, I need X, I'm using that last equation. And so another important thing to keep in mind when we're doing kinematic questions, velocity and displacement are vector quantities and have direction, while speed and distance are scalar. So it's only the magnitude. Direction doesn't matter. So I have a question for you then. You wake up at 8:29, it's speed walk because you're late, 100 meters south to Chernoff. You get there at 8:31, realize you're late, you decide to go 100 meters north back to bed. By 8:34, you're snug as a bug in a rug, dreaming of distance. So I want you to find the velocity, the speed, the displacement, and the time. Sorry, the distance. I'll give you a few seconds, a little while to work on that. In the first half of the question, it takes you 2 minutes to travel 100 meters south. And then it takes you 3 minutes to hustle back, do the same 100 meters. So your total distance is 200 meters, and the total time it takes 5 minutes. Correctly stated, your displacement, 0 meters. Your speed would then be your total distance traveled, 200, over your total time, 5 minutes, giving you 40 meters a minute. I think it's pretty fast. That's like Usain Bolt territory. And then if your displacement is 0, well, your velocity has to be 0. So that's a simple concept question, just testing scalar versus vector quantities. What's one special thing about a vector quantity? How do you know a number is a vector and not a scalar? Yep. Yeah, it's got direction. And it'll have an arrow on it. So here's a bit of a complex question for you. I guarantee this is harder than anything you'll find on your exam, but it tests all the skills you need to answer any question that could appear on your exam. Here's a case for your approval. A car traveling 198 kilometers an hour speed, going east, passes a stationary police car. The car throws its donut out the window, fumbles with its keys, and after 10 seconds, begins accelerating at a rate of 6 meters per second squared east until reaching 18 kilometers an hour east above the speed of the car. The cop then continues to travel at a constant speed until reaching the speeding car. And I want you to find out, how long does the entire chase last? Yep. 180 seconds. That was the fastest mental math I've ever seen in my life. The answer, yeah, 180 seconds is correct. For the rest of us in the room, what I really want to emphasize on this is that a lot of people, even if they have the kinematic equations ahead of them, they'll look at this question and get confused that's where a lot of people in this class sort of get stuck. And so you really just need to think about how to tackle the question firsthand. And you described it very perfectly in saying that, let me just go to the next slide here. So you converted kilometers an hour into meters per second, because you always want to be dealing with the same units. And since I've given you acceleration in meters per second squared, it's easier to, there's less calculating manipulation if everything else is also in meters per second. And the next thing you did was sort of conceptualize the distances traveled by the two vehicles. So on the bottom here, we have a speed time graph, right? And does anybody know the integral of a speed time graph? What do you get when you multiply speed by time? Yeah? Distance, exactly. So the area of this rectangle is the distance traveled by the car. And so the car, we said, was going 55 meters per second the whole journey. It never stopped, it never changed, it never slowed down. The cop, on the other hand, had a 10-second delay. Then it began accelerating to 60 meters per second, and it maintained that until it caught the car. So now you have that as a concept in your brain. Now it's time to create a formula that describes the area of these shapes. And to do that, you can say, well, x traveled by the car is equal to the speed of the car times time. And I've added plus 10 to indicate the difference in starting times between the cop and the vagrant, i.e. me and my car. The cop, the distance traveled by the cop, you can separate into these two areas, the triangle and the rectangle, x1 and x2. And so the net, calculating the area here, what I've done is I've got the 60 meters per second times the full time and the time between 10 and the end. And then you have to subtract the time when it was accelerating, that it was not going 60 meters per second. And that's where the second half of this equation comes in, v squared divided by 2a. And if you're curious about how I got that, let's go back to our kinematic equations. We needed x, and what equation has x? This one. And we had the final speed, and we had the initial speed. Initial speed was 0, because the top starts from rest. And I told you that the final speed was 60 meters per second, and I gave you the acceleration being 6 meters per second squared. So you had everything in there to find the distance it took the cop to travel to accelerate to that final speed. And as you rightly pointed out, when they catch each other, when the cop catches the car, they're going to have traveled the same distance. So you can say that the distance traveled are equal. So you can set those equations equal to each other. And now you just fill in the numbers that we had. So the speed of the car, speed of the cop, acceleration. And that's just a bunch of calculator number crunching. Reduces down to 55 times the time plus 550 equal to 60 times the time minus 300. Simplifies even further. And you get 170 seconds. But remember that I said t starts at 10 because that's when the cop started chasing. This is because we took it away before we had added that. So now we have 180 seconds or 3 minutes. And at first glance, it's probably a lot. But does everybody see how I got the 180 seconds in the end? Anybody want me to clarify anything? Yep.
Why do you subtract them?
For the cop here? Yeah. So what I did is I said the cop, so V of the cop, I said was the final speed, 60 meters per second. And I multiplied that by the time of the chase. So from here to here. But he wasn't always going 60 meters per second. It takes time for him to accelerate to that speed. And so what I did is I subtracted the distance it takes to accelerate to that speed from this section of the area. So now instead of having just 60 times the total time, you have from here to here and whatever it takes to accelerate. Does that make sense? Okay. Did I see a hand up there or just an itchy head? Gotcha. All right. Still no questions from the Zoom crowd. If you can't hear me, just shout. So I've got another part B for you. After what distance will catch the car. You have the time of the chase. Now it's time to find the distance. You said the distance the car travels is equal to the speed of the getaway car times the time he was driving, or she. We're going to quickly transition to 2D vectors in relative motion. So here's a plain question for you. There's a good chance you'll have something similar to this on your exam. They tend to love these ones to describe vectors. So here is the example. A plane encounters 60-kilometer-an-hour winds from the southeast on its way to London. At what velocity relative to the air must the plane fly to maintain a velocity of 500 kilometers an hour west to the ground? And wind's coming from the southeast, which way is it going? You pointed it. You want to say it? Yep. Northwest? That's right. That's sort of one thing I always despise. They try to throw something in there to make it to trip you up. If something's coming from the southeast, it's headed northwest. Another thing that's really important that I should definitely mention, even if you don't know an answer, you can get away with some partial marks, exclusively for declaring direction somewhere on your page. Anytime you write something that has vectors in it, you have to declare what way is positive. So in this case, I'm saying west is positive and south is positive in the y direction. First of all, what are we solving for? Yep. Yeah. And how can you express the velocity of the plane relative to the air in terms of the other velocities that I have given you? Yeah. Did you say this, VPE minus VIE? Yeah, that would be correct. So you've made it that far. What's your next step? And are we all familiar with how to find the x and y components of the vectors? Well, if it's true that VPA is equal to VPE minus VAE, you can say that for the x direction. If you can say that for the x direction, we know that the velocity of the plane relative to the Earth, we want to be exclusively in the x direction, 500 kilometers an hour west relative to the ground. But we know that the wind is not going perfectly up and down or left and right. It splits the middle. So when something's going northwest, it's going smack in the middle of north and west. That's 45 degrees. That's where I got the 45. And if we're looking for the velocity of the air relative to the Earth in the x direction, we will use our cosine rule, adjacent over hypotenuse. So we can say that the velocity in the x direction is equal to the resulting vector, 60 kilometers an hour, multiplied by cos of 45 degrees. And that gives you about 42. Did anybody make it that far? I got a couple nods. That's how you do it in the x direction. Using these numbers, you can solve for the velocity of the plane relative to the air in the x direction. Just a little over 450 kilometers an hour. If you can say that about the x direction, the same can be said about the y direction. And we know that the resulting velocity of this plane relative to the Earth, it's not moving in the y direction, so 0 kilometers an hour. The Earth, that should be the air relative to the Earth. I swapped the E and the A. It's 60 kilometers an hour multiplied by sine 45, because now we're doing opposite over hypotenuse. You'll notice it's the same number, only there's a negative. because we assign down, south, as the positive y direction. Therefore, up would be negative, north would be negative. So using these numbers, we can plug them back into the normal formula we just used, and we get 42.43 kilometers an hour in the y direction. Who wants to take a stab at how, now that you have in the x and in the y, how would you find the resultant vector? Yes. Absolutely you do. So this is a trip back to elementary school, or whenever we learned it, to be honest, I forget. A simple plug and crank, square those numbers, and then take the square root. Be very mindful on your calculator not to do the square root of just the second number. And that'll give you an answer. That'll give you 459.53 kilometers an hour. That's not enough for an answer. That's insufficient because we don't know where the plane's headed. We just know that it needs to be going this speed. You have to give it some kind of direction because you need to answer with a vector. So if we have the speed in the x and y direction, how do you go about finding the angle of flight? Yes. Tan function is correct. So we can say tan theta, theta displayed on the graph there, is equal to the y direction divided by the x direction. Plug that into your calculator and get 5.3 degrees. So then our final answer, including the vector notation on the velocity variable, 459.53 kilometers an hour west, 5.3 degrees south, because it's 5.3 degrees below the horizontal. Is that clear how we arrived at both a magnitude and an angle? So the answer at the end here, if theta is correct, I accidentally put 542 instead of the old number. I'll change that for everybody's going to get a copy of the slides along with the recording. So before you get that, I'll change that. Thank you for pointing that out. Sorry, where did the 45 degrees come from? So when somebody tells you that something is going exactly southeast or exactly southwest, it's splitting south and east or south and west, and it's going smack in the middle. There are 90 degrees separating west and north. So if you're going northwest, you're going 45 degrees above west. That's where I got the 45. Hopefully that makes sense. And hopefully you can hear me. Let's talk about forces. Forces are measured in newtons. 1 Newton is 1 kilogram meter per second squared. You might recognize some pieces of that. Kilogram is mass, and meter per second squared is acceleration. Gravitational force. This is one number you'll have to keep in mind. I'll send you the recorded copy, so you're not missing it. Gravity is 9.8 meters per second squared. Let's get to Newton's laws of motion. Does anybody know Newton's first law of motion? Off the top of your head? Well, it's an object will continue at constant velocity or remain at rest until a force acts on it. Newton's second law of motion, one we're all familiar with. Force is equal to mass times acceleration. Newton's third law of motion, for every action there is an equal and opposite reaction. Some people have a tough time figuring this one out in their head. So here's an example. If you, I don't know, for whatever reason, need to move a rock and you've tied a rope to it and you're yanking on it with all your might, let's say 250 newtons of force, and the rock doesn't budge, well, that means the rock is holding you in place. The rock is pulling the rope to keep you stationary. So if you're pulling with 250 newtons, that means the rock is also pulling with 250 newtons of force. It's a net zero. Total tension in the rope, 250 newtons. But here's another scenario. Imagine you're playing, you made it to Squid Game or some, I don't know, I've only seen one episode. And you're yanking on the ropes equally with 250 newtons of force. How much tension is in the rope? This could be like a multiple choice question. Yep. 250 newtons precisely. And if, say, the orange fella was given any less than 250 newtons, you would be yanking him and the rope to the right. Let's get more into forces. Let's talk about frictional force. A force exerted due to friction, described by the equation, force of friction is equal to mu times the normal force. Mu is the coefficient of friction. So I've got a question for you. There's a block on a ramp. The ramp has an incline of 25 degrees. And I'm going to ask you, what is the coefficient of friction? Then you can round to do decimal places. Who wants to tell me what forces are acting on this block? Yep. Of course, gravity's acting on the block. What's keeping it on the ramp? Yep. Friction's keeping it on the ramp. What else is there? Yep. Absolutely. If there's friction, there's a normal force. So let's, I'll give you a little bit to think about it. If anybody has an idea how to go about solving it, throw up a hand, say something in the Zoom chat. Is anybody troubled about thinking about the mass of the block? That's a good instinct for a lot of people have. But I think the more we dive into this, you'll find that you don't need the mass. So correctly stated, there are only three forces acting on this block. There's gravity, the normal force, and the frictional force. Force of friction is always going to be pushing the object uphill. You'll have a bunch of questions where it'll tell you that friction's involved, and you don't know if friction is pushing it down or up. Well, if gravity's pulling this block down, then the only direction the force, the friction's going is up the ramp. There's no sliding, so there's no net force. Net force is zero. So we can say that the force of friction is equal to the force of gravity parallel to the ramp. And this is how we can draw that. If you break it into its components. And then we can build this equation where we can say the force of friction, which is mu times the normal force, is equal to the force of gravity times sine 25, which will give us the force of gravity parallel to the ramp. Anybody uncertain about why 25 is the right angle? Clear as mud? Well, I'm going to explain it anyway because I made the slides. So here's your block on the ramp. We got a magnifying glass. We're up close. We've got the force of gravity, split it into its components. Notice that these two lines are parallel, the ramp and the force of gravity in the parallel direction. These angles are denoted as right angles. So you don't have to be a mathematician to see that the top angle there is 90 minus theta, and therefore the angle within our force diagram is going to be the same as the elevation of the ramp. And that's true for any case you have involving ramps. So save you time thinking about this whole process. You can just instantly say, I know that the angle between the force perpendicular and the force of gravity is going to be the same as the elevation of the ramp. We can confidently say that. So then we have that equation. We similarly can say that the The normal force is equal to the force of gravity perpendicular to the ramp, since the block is not flying up or through the ramp. So we fill that in for the normal force, and then we can say, sub in these this cos relationship. And the force of gravity is going to cancel out because it's in both terms. We don't ever need the mass in this question. And we're left with mu equal to tan 25. And how did I get tan? I said mu is equal to sine 25 over cos 25. Sine over cos is tan. That gives you 0.47. Hooke's law is what describes the force acting on an object due to elasticity. There's the equation for it. The spring force equal to K. K stands for constant, I guess, spring constant. And it's measured in newtons per meter. So I guess the way you can think about it is how much force does it take to compress or stretch this spring 1 meter? That is what the spring constant is. And then delta x is the displacement from the resting point. My friend here, Ashraf from the Toronto Zoo, weighs 250 kilograms. Good guy. He sits on your couch and sinks 50 centimeters into the sea. And I want you to find the spring constant of the coil in the couch. Hey, anybody want to start us off by telling me what forces are acting on this animal? Yep. Pardon me? Force of gravity is one of them. What else? Yep. Normal force. In this case, what is the normal force? What's pushing up on it? It's the spring. So there are two forces involved. Downward gravity, upward springs. And so we have our two equations there. So I heard most of that. You're saying you can make the spring force equal to the gravitational force? Absolutely. That's the right step. And so if you line that up, we can say mg, the mass times gravity, is equal to that constant times the depression of the spring, the stretch or contraction. Rearrange for the spring constant gives you mg over the distance. And you have those numbers. I gave you the weight. You should know 9.8 meters per second squared off by a head. And I told you 50 centimeters he sank into the couch. That's half a meter. And so the answer you should get, 4,900 newtons per meter is the spring constant. I have no idea if that's strong or not. I wrote this question not knowing if animals sit on couches. Yep. The spring constant is expressed in newtons per meter. And we know that a newton is a kilogram meter per second squared. So if you were to put the guy's weight into grams instead of kilograms, you would have to change the units you use for your spring constant. You couldn't say newtons per meter anymore, right? So you have free will to do that. Usually, keeping everything in the international standard units, the kilogram is easiest. You might have a question where they request it in grams because perhaps you're dealing with watch springs that have much, much smaller spring constants, right? So read the context of the question. I would normally keep it in kilograms. So let's talk about Guy Fieri and perceived weight. So the mass and weight are two different things. Weight is relative, which is what I tell my parents. Mass is measured in, is a relative expression of mass, and it's measured in newtons. The weight we feel is equal to the normal force acting on us. So generally speaking, we only ever experience gravity and normal force when we're just standing around. And they're equal opposites because we don't float off into space and we don't fall through the ground. If ever they were not in equilibrium, we'd be falling or jumping. So sometimes though, when we experience external forces and accelerations, there's a mismatch in gravity and the normal force, and that's how we feel lighter or feel heavier. So suppose you're in an elevator. You tend to feel heavier accelerating upwards. That's just the floor beneath you is lifting up into your feet. And the opposite is true when falling downwards because the floor is escaping from beneath your feet. Feel lighter. And there is would the force of spring be equal to the gravity? Yep, you got that from the last slide. Sorry, I didn't check that quickly enough. Thank you, Faith. So here's a question now about perceived weight. Ashraf is back at it again. By the way, he's a Malayan tapir. There aren't too many of them in the world. At the time I made these slides, which was a couple weeks ago, there were 3 left in North America, and Ashraf is one. Anyhow, that's not going to be on the exam. So if he's in an elevator and it's accelerating at 4 meters per second squared, what is his apparent weight? You can go ahead and just focus on the animal here. Don't worry about the weight of the elevator. First off, who wants to tell me if it's going to be heavier or lighter than his normal weight? Yep. It's going to be heavier, yeah. And you know that because accelerating upwards, the normal force is going to be much higher than force of gravity. Also, if you're hunting for partial marks, it's always nice to draw free body diagrams. You'll never lose marks. Even if you do it wrong, you'll probably get partial marks. Anybody want to tell me his apparent weight, i.e. normal force? And so another thing too, I really need to emphasize, always include positive directionality in your answers. So in this case, I'm saying up is the positive y direction, and we're saying that the net force experienced by the animal is equal to the force of gravity and the normal force. And if the net force is mass times acceleration, which would be the acceleration of the elevator, the whole thing, that's equal to the mass of the animal times gravity plus the normal force. Whoa, what did I do? Okay, cool, it's back. So you plug in those numbers because I've given you everything. Notice this time I've declared gravity as negative because I declared up as positive y direction. And so when you crunch that in your calculator, you get 3,450 newtons. So here's a part B to that question. Unfortunately, he's too heavy. He exceeded the weight limit, and the elevator goes crashing downwards in free fall. What is his apparent weight now in free fall? Apparent weight is always equal to the normal force. And if you're in free fall, that means there's nothing pushing up on you. You have no force acting on you but gravity. You're freely falling, as they say. And that's when you experience weightlessness. So in reality, I keep doing that. He weighs nothing and he feels weightless. So it's sort of a trick question in a way, because you can answer it as soon as you read as soon as you read the word free fall, you can just say 0. But you can also calculate it mathematically if you stick to the same formula and say that the net force is equal to forces acting on them, the only force being gravity. There's no normal force. Does that make sense in everybody's head? Sometimes that's hard to. Yeah. We're going to break into work and energy. And I apologize because this question has no reason being this difficult. It's a bit of a tough question that you won't necessarily encounter on your exam, but the idea is that it's making you think and it's making you use these equations. So quickly, what is work? work is the amount of energy used to displace an object parallel to the applied force. So we can put that into an equation. We could say W, that's work, is equal to the force applied times cos of theta. Theta is the angle between the force applied and the direction of movement, and D is the amount of movement. And we give this, we give energy its own unit, the joule, and joule is Newton meter. So here's a question. I don't know who named your dog, but Kyle sees a butterfly, and he runs after it, pulling the leash with a force of 200 newtons. You pull with a force of 150 newtons on the leash, which makes an angle, a 30-degree angle with the ground. Kyle stops dragging you after 10 meters. What is the work you do on Kyle? And what is the work Kyle does on you? First of all, who's doing positive work? Who's doing negative work? Yeah. Absolutely. And you know that because? Perfect. Kyle is pulling in the direction, pulling you in the direction that the force is applied. You're applying force in the opposite direction of the net movement. Therefore, you are doing negative work on your dog. So let's look, we'll look at them separately. Here are two little graphics here that might make it a bit easier to understand. So the work you do on Kyle, you're pulling with 150 newtons. You don't want to be subtracting any forces. You're not looking at the combination of forces because work doesn't refer to any of the net force or anything like that. You're looking at exactly how is the force being applied separately. So in the first case, the work you do on Kyle, you're yanking with 150 newtons. And if the leash makes a 30-degree angle with the ground, that means you are pulling at a 150-degree angle from the direction that the dog is dragging you along the ground. In this case, you're getting dragged perfectly horizontally to the ground. So then our equation comes to force, which is 150 newtons times cos 150 times 10 meters you were dragged. And that gives you an answer of negative 1,300 joules. Does it make sense how I got to 150? It's, you can sort of see from the picture. And the work Kyle does on you, you would use an angle of 30 degrees. It's 30 degrees below the horizontal in this case. And so 200 newtons is what the dog's pulling, cos of 30 degrees times 10 meters. And that gives you 1,700 joules. So the reason I like this example is because it shows that it's not exactly equal opposites, right? Just because you're in the same scenario and you get dragged 10 meters, the dog ends up doing more work. It's all dependent on the angle in this case. The concept of applying work at an angle to a direction is very closely tied to torque, which we're going to get into soon. So this is sort of an intro to that, I suppose. But let's for now keep with energy and work. Energy comes in a few flavors. You've got mechanical energy composed of, for our purposes, gravitational potential energy, which is mass times gravity times the change in vertical position elevation. Elastic energy, which we touched on briefly with elastic forces, is equal to K, the spring coefficient, times the movement of the spring squared. And kinetic energy, moving things like kinetic energy, that's equal to 1/2 mass times speed squared. Power is energy per time. It's measured in watts. Watts are therefore Newton meters per second. And doing a quick unit analysis, you can also say, therefore, that power is equal to force times speed. If you work those units out, force being newtons, speed being meters per second. 1 watt is 1 Newton meter per second. So here's another question for you about the conservation of energy. So a 50 kilogram roller coaster cart passing point B at 35 meters per second. I want you to find the height at point A and the speed at point C. Then I want the cart is going to be stopped by a spring at the very end. The spring has a constant, spring constant of 150 newtons per meter at point B. And I want you to tell me what distance it takes for the cart to come to rest once it hits the spring. So let's start on A and see if somebody can tell me the height at point A, or better yet, if somebody could tell me without numbers, just plain and simply, how to even go about thinking about this kind of problem. Yeah, you're absolutely true. Yeah. And for those that didn't hear, so the total mechanical energy at points A and B are the same. And I tell you that at point A, the cart's not moving. So all of its energy is stored in gravitational potential energy, part of which is converted into kinetic energy, because at point B, it's moving 35 meters per second. But bear in mind that at point B, it's also elevated 10 meters. It hasn't dropped to 0. So you have both gravitational potential energy and kinetic energy. What kind of, well, I already told you, I suppose, at point A, you only have gravitational potential energy. Who wants to tell me what the total energy at point B is? Slowly reveal more and more as we inch towards an answer. So for point B, you have all of the numbers that fit the variables in that equation. It's a number cruncher. So to test if your calculators are working, who wants to give me an answer for the energy, total energy at point B? You get this one? Yeah. Look at that. But now that we have this number, we can use it to find height at point A, because we know that the energy at point A is going to be the same. And we know that the only energy at point A is going to be gravitational potential energy. The speed is 0. No springs in sight. So we can say that the mass times gravity times the height is equal to a little over 35,000 joules. Punch that into your calculator. You get 72.5 meters. So that's pretty tall. Your next question is going to be the speed at point C, where the height is now 0 meters. And using what we've just used to find the height at point A, I'll let you sit for a moment and try to find the speed at point C. Let's walk through the numbers here. Speed at C, we're saying there's only kinetic energy. I wrote EA, that should say. EC, that's another typo. I'll fix that as well. So now we have 1/2 mass times velocity squared is equal to this energy we found that's going to be the same at all points. And you said 37.7? Awesome. Anybody else get that? Killing it. So now the second half of the question, you solved some necessary information that you're going to need to use for the second half of the question. You're trying to find how long it takes for the cart to stop once it hits the spring. And you do have the speed, and you have the total energy at point C. What happens when the cart hits the spring and stops? In terms of energy vocabulary, where is You have this moving object with a lot of kinetic energy, it hits the spring and stops. What is happening in terms of energy? Exactly. And is it, what proportion of the kinetic energy is converted into spring potential energy? Absolutely. When it hits 0 meters per second, all of the kinetic energy has been converted into elastic potential energy held in the spring. So to find the stopping distance, we're going to need the spring energy equation. And so with this, the first line here says the energy at point B is equal to the kinetic energy at point B plus the gravitational energy plus the spring energy. And the only one that counts because it's not moving and it's at 0 meters is spring energy. So we're reduced to K times X squared. And we know two of these numbers. We know K is 150 newtons per meter, and we know total energy is 35,525. Who has an answer for X? So what number do you get when you have when you include the 1/2 ahead of it? 21.8. Anybody else get 21.8? Yeah. Okay. Ta-da, you got the answer. Okay, so let's now talk about impulse and momentum. Momentum is the force an object possesses at a given moment, hence momentum. It's described as P with the vector notation equal to mass times speed, or sorry, excuse me, velocity, hence the vector notation. Impulse is the force imparted as momentum changes. And we can say, you write the word impulse because there's no technical variable describing impulse. Or you can write it as delta P with the vector notation because impulse is the difference in momentum. And that's equal to the change in force multiplied by the time. Which you can rearrange. You can say the change in force is equal to the impulse divided by the time. Therefore, increasing the time of contact reduces the force exerted by an object as it changes momentum. And what I've written there is, as t approaches infinity, as t increases bigger and bigger and bigger, the force experience approaches 0. So what's a way of conceptualizing that? Old cars in the 1950s, there are these big steel boxes. So when you hit a tree post, there was no crumpling. The whole car just stopped dead. And if you were wearing a seatbelt, you'd be shredded like pulled pork. And if you weren't, you'd fly through the window. A lot of force was exerted in the rapid change. However, these days, they make them out of very pliable materials. So if you crash into a tree, the whole front of your car would just mangle. And what that does is it increases the time of contact. So less force is exerted on your body. Here's a question for you. I serve a 1/4 kilogram tennis ball at 20 meters per second. Eugenie Bouchard hits the same ball back in my face at 30 meters per second. If her racket makes contact with the ball for 1/2 second, what is the force that she exerts on the ball? And as always, when you're starting a question with vectors, what's the first thing you do? That's a good way to start. So we can say that towards my face is the positive x-axis. I'll put down the equation for change in force. The force she exerts on the ball you're trying to find. What's the change in speed? Ball, yeah. 50 meters per second is correct. And I gave you the mass. We just declared that the change in speed is 50 meters per second. And the time of contact between the racket and the ball is 1/2 second. You now have all the numbers to plug into this equation. Does anybody want to tell me what the answer is? Anybody get 25 newtons? Sweet. Let's head on to, we did energy, now conservation of momentum. In collisions, momentum is always conserved. Notice energy might not always be conserved. Momentum always is. And here's a quick equation for that. You can say final momentum equal to initial momentum. Break that down into components. And you are using the final speed of the first object. That's what V1F is. V2F is the final speed of the second object. And V1I is initial of the first object. V2I initial speed of the second object. And this applies in all directions. So when you split things into components, you have your X and Y variables, and you apply the equation into the X and Y as well. And so some people are confused about the differences between different types of collisions. This will probably be anything multiple choice question, or they might say, you know, you solve a momentum question and it'll ask you what type of collision it is. You know, elastic, inelastic, perfectly inelastic. And there are a couple ways to know. In an elastic collision, energy is conserved, so is momentum. I like to think about it like this. The two objects hit each other and are repelled. There is no loss in energy during the collision. In an inelastic collision, energy is not conserved, momentum still conserved. And oftentimes you can know it's an inelastic collision because when they collide, both objects will move in the same direction, but they do not stick together. That's a pretty good rule of thumb for inelastic collisions. And that means that energy is being lost during the collision. How can energy be lost during the collision? Often the sound. You almost never hear of an elastic collision because if I were to drop a bouncy ball from, say, you know, a couple meters, it would bounce and it wouldn't come back up a couple meters. And reason for that is that you would hear the ball hit the ground. When the ball hits the ground, energy is lost to sound. So when it comes back up, it doesn't come back as high. Looking at perfectly inelastic collisions, energy is not conserved. Momentum, however, is always conserved. And the objects stick together. And I always think about it as when two cars collide and they become entangled together, that is a perfectly inelastic collision. So now here's a question that'll test some of that knowledge. So suppose a bullet, and I give you the mass of the bullet in grams, is fired at a wood block, and there's the mass of the wood block. The block is hanging from a string, and the bullet embeds in the wood, and the block swings 0.225 meters. What is the speed of the bullet? So let's think about what kind of collisions are occurring here. Who can tell me if it's elastic, inelastic, or perfectly inelastic when the bullet strikes the wood? Exactly. It's perfectly inelastic because the bullet and the wood block become one mass. Absolutely. So for those who couldn't hear, thinking about how you're going to answer the question conceptually first is essential. What she said was, we know the height that the block travels once the bullet embeds in it. And we know that once it reaches that height of 0.225 meters, we know that the bullet and the block together are stationary. That is the peak of its swing. So you could calculate, because the energy at this peak of its swing will be the same, will be the same as when the block is stationary and hit by the bullet. So you can determine the speed at which the block swings based on the gravitational potential energy when it reaches that apex. And then from that, you could go ahead and find the speed of the bullet. So we can start by saying to the right, positive x direction. Conservation of momentum is going to come into play, and there are a lot of confusing tongue twisting variables. B for bullet, BL for block, BBL for bullet block. And so we can say that the mass of the bullet times the speed of the bullet is equal to the mass of the block times the mass of the bullet times the speed of the bullet plus the mass of the block times the speed of the block, stationary initially, is equal to the mass of the bullet and block combined times the speed of the bullet and block combined. So in determining the speed of the bullet, we just simply rearrange the equation. Unfortunately, we don't have the speed of the bullet block mass together. We need to find that. And we can use conservation of energy principles to find that, as we described earlier. So E will say that the kinetic energy of the bullet and block together as it's struck is equal to the gravitational potential energy when the bullet block complex is no longer moving and it's reached its apex. So we can reduce that even further by eliminating the mass of the bullet and block from the equation. I moved the 1/2 from the left side of the equation. It's now on the right side is the 2 there. So and so if we isolate for the speed of the bullet block, some quick calculator punches, we get 2.1 meters per second. So now we can go back to our conservation of momentum equation, and we can sub in the speed of the bullet and block into that equation. And we know that the mass of the block is 1.5 kilograms. The mass of the bullet, 9 grams. That turns out to 0.009 kilograms. Multiplied by the speed of the two once they've collided, and all divided by the mass of the bullet. So who wants to tell me what the speed of the bullet is? Pretty fast, huh? Yeah, perfect. Is anybody confused about why I used conservation of energy for the second half, but conservation of momentum for the first one? In a perfectly inelastic collision, as I described, energy is not conserved, energy is lost. So there's some loss in energy to external things, sound, light, whatever, heat, when the bullet strikes the wood. However, once the bullet has struck the wood and is embedded in it, conservation of energy still applies, because now it's the two things moving at a certain speed, and that speed is translated into gravitational potential energy. So there's no loss in energy there, it's just a conversion. But initially, because we described it as an inelastic collision, you cannot use conservation of energy principles to describe the energy as the bullet is fired and as the bullet and block swaying together. That make sense? That's my voice. Angular motion. Moving in a circle means your velocity is changing because it's changing direction. Which means if you're changing direction, you're accelerating. This acceleration we describe as speed squared divided by the radius of curvature of the circular motion. The acceleration always points to the center curvature. And since we say that force is equal to mass times acceleration, we can say that this angular force, which we call centripetal force, is equal to mass times speed squared divided by the radius of curvature. And that little W thing is omega. We use omega to represent the angular rotation. And you can calculate that by the speed, meters per second, divided by the radius. Is anybody confused about how we derive v divided by r is equal to angular rotation? Angular rotation being the angle, the number of degrees that change per unit time. So you would have theta over t. And when you have that angle in radians, you multiply that by the radius to get what portion of the circumference has been traversed. Somebody mentioned specifically banking questions they have troubles with. So here is a bank question. You're designing a circular curve in a road where the speed limit is 70 kilometers an hour. If the incline is 25 degrees and the coefficient of friction between the tires and the road is 0.25, what radius of curvature will be safe for people driving 20 kilometers an hour over the limit? And I've presented you with a free body diagram. We have gravity, friction, and the normal force, the centripetal force as well. Anybody want to tell me why the force of friction is pointing downhill? Absolutely. And so the rationale there is that if you're pushing the pedal to the metal, the tendency will be for you to fly upwards on the curve, and friction naturally resists that. And so friction is pointing downwards on the curve. Think about that. Somebody in the chat says, conservation of momentum. Where did the mass and velocity go? I'm going to cycle back to that real quick. Question was, where did the mass and velocity of the block go? Right. So in a perfectly inelastic collision, when the bullet becomes embedded in the block, they become one mass unified that travels at the same speed. So I haven't eliminated the mass or speed of the block. What I've done is I've combined them. And so we have the mass of so BBL is the bullet block. So we have the mass of the bullet and block and the speed of the bullet and block. That's where they go. So does that make sense? Here we go. Cool. Let's back to this one. The cryptic part of this question is it says what radius of curvature will be safe. And so if you make the radius smaller, that means you need to be going slower. Exactly. So the idea is you're working your way from large to small. So you're working inwards. And so you're looking for the maximum size of the radius. Yeah. So then if you were looking for the minimum radius, it would be the opposite. Yeah, very an astute observation. So for this directionality, we're going to be saying x is to the left, y is positive upwards. Some unit analysis here, 70 kilometers an hour plus 20 kilometers an hour is 90 kilometers an hour, and that in meters per second, 25. I'm asking you what radius of curvature will be safe for people driving. And what does it mean to be safe while you're driving? It means that the car is not sliding in any direction. So we're going to try to balance these forces to ensure that the car, represented by the black there, is not moving in any direction except, along the road. So to do that, we're going to break our forces down into vertical components, the y components. And we're going to look at the sum of vertical forces acting on the car. And since I declared up as positive, we have the normal force in the y direction, subtracting the force of friction in the y direction, and also subtract the force of gravity. And since the net force is 0, because we don't want the car to fly anywhere, we can rearrange and say that the normal force is equal to frictional force plus the gravitational force. The normal force is equal to, in the y direction, is equal to the normal force times the cos of 25. And again, about finding that 25-degree angle. It's the elevation of the ramp I've given you. And of course, force of gravity is mass times gravity. And so you can rearrange to try to solve for the normal force. And so we're left with this equation that the normal force is equal to the mass times gravity divided by cos 25 minus coefficient of friction times sine 25. We can't take this any further because what do you do with mass, right? I don't know. And it would be a useless venture if you did this calculation and determined the proper radius of curvature for one specific mass, right? So you want to make sure that it applies to all shapes and sizes on the road. So we're going to need to start looking at the x direction as well. So I've broken up these forces into the x direction. So we can say the sum of the forces is equal to the normal force in the x direction and the frictional force in the f direction. Also remember that the net force in the x direction is equal to the centripetal force, which is always pointing inwards into the center of curvature. So we can say that centripetal force therefore is equal to the normal force in the x and the frictional force in the x. And we know that centripetal force is mass times speed squared over r. And we know our equations for normal force and frictional force in the x. Those are them there. And again, this becomes a mission to rearrange. All I did here was rearrange for r. And because the radius of curvature is what we're trying to find. And so again, we stop because we don't have mass. But we can use, we found the normal force in our first equation. And we can sub that in to the second equation we derived, the normal force. So now we have this big, long, cumbersome line to put on our calculators. The mass times the speed squared divided by that massive line there. And you'll notice mass cancels out. And we don't need it anymore. And now we're just left with numbers that we have. Does any brave soul want to try to put this in their calculator? Anybody? 78.7. And what units are those in? All right, let's talk about gravity. All objects, no matter how big or how small, have a gravitational pull relative to their mass, described by this equation. The force is equal to the gravitational constant, G, times the product of the two masses, divided by their radius of separation squared. And your gravitational constant is given there 6.673 times 10 to the negative 11 will be enough if you memorize that, but you'll have it on your formula sheet. So. Big deal. Another thing to note that the radius is always described from the dead center of the object, the center of mass. And that'll come into play in this question. So say you want to, say it's 2018, you missed last year's Game of Thrones, you want to get HBO for free. So you launch a 60-kilogram satellite that orbits the Earth at 220 kilometers above its surface. At what speed must the satellite be programmed to travel to stay in this orbit? And I've given you a couple numbers there. First one is the radius of the Earth, 6,380 kilometers. I've also given you the mass of the Earth. And so we'll walk through that answer then. Does anybody have a number? Okay, I'll just go slowly. Rightly, as you said, the force, the centripetal force is going to be equal to the only force here, and that's the force of gravity. We can express this with more variables to say that the mass of the satellite times the speed of the satellite squared over r is equal to this force of gravity, which is the gravitational constant multiplied by the mass of the satellite times the mass of Earth, all divided by the radius of separation squared. And who can tell me why I didn't just use mg? Yeah. Exactly. Believe it or not, you weigh different here versus St. Catharines or Mount Everest. It's a distance-dependent force, and so the only reason it's not big news that people weigh less on Mount Everest than sea level is because it's such a small difference in elevation that we don't notice it. But when you're 220 kilometers above the Earth's surface, you start to notice it. So I've given you the radius of the Earth, and you've got to add 220 kilometers to that because you're above the surface of the Earth. You'll notice that the couple variables here cancel out, the mass of the satellite, as well as one copy of the radius. So we have v squared being equal to the gravitational constant times the mass of the Earth divided by the radius of separation. 7, 7, something, something. 7, 7, something, something sounds right. Oh yeah, it spins. I forgot I made that. It goes on forever. Okay. Guy Fieri's back. In preparation for when Elon Musk's robots destroy all human life and what will be known as the Great Readjustment, you decide to flee Earth and live on a space station. If the distance from the center to the rim of the station is exactly 100 meters, at what speed must the rim rotate to match the gravity experienced on Earth? And I've given you a head start by telling you that the normal force is equal to the centripetal force. Yeah. So you were, for context, you're standing on, so suppose it's a bike tire. I'm trying to speak in metaphors so Zoom understand. If you're, you'd be standing on the rubber part of the bike tire while it spins. And when you're in space, let's just ignore the effects of other planets and gravity and stuff. We're just talking about spinning in isolation in a vacuum. And so we can say that mass, your mass times acceleration that we would normally feel on Earth, which we know is 9.8, is equal to your mass times your speed squared divided by the radius of curvature. So plug in 9.8, plug in the radius, the mass is irrelevant, it cancels out. You're left with another algebra problem. And if your thumbs don't slip, you should get 31.3 meters per second. Okay, let's talk torque then. Torque, symbol tau, each letter, used to represent torque. And it's equal to the perpendicular force applied to an object multiplied by the distance from the fulcrum, which is the pivot point. Torque is pure memorization. Torque is positive when rotational motion is counterclockwise. It's negative when it's clockwise. And that's just convention by default. Calculating center of gravity. What you do is you multiply the mass of an object by its distance along a plane, and you take the sum of that for all of the masses that you are evaluating, and you divide that by the total mass. So here's an example for you. You have a 10-meter stick. On that stick, you have a 5-kilogram weight at the 3-meter point and a 15-kilogram weight at the 8-meter point. I'm asking you to find the center of gravity. We can do this in our heads. We can walk you through it. We got The equations, you do the mass times the x distance. So you would do 5 kilograms times 3 is 15. Keep that in your brain. 15 plus 15 times 8 is what? 120, I think. Yeah, cool. So now you have 15 plus 120 is 135. 135 divided by 20. Yeah. 6.75 meters. So from the left, count 6 3/4 of a meter. That is the point at which you could lay the stick on a pin and it will balance perfectly. That is the center of gravity. So let's get into more practical applications of torque. Guy Fieri was in my mind when I made these. He's 6 meters up a 10-meter ladder that's resting against a frictionless wall. The ladder weighs 100 newtons. If he weighs 850 newtons, what is the minimum coefficient of friction between the ladder and the ground? Who wants to tell me what forces are in play? Well, first of all, let's assign directionality. I'm going to say down is the positive y direction. I'm going to say right is the positive x direction. And of course, we know counterclockwise is the positive torque direction. What forces are acting on the ladder in the horizontal direction? Precisely. There are only 2 forces acting in the horizontal direction. Here they are. Force of friction keeping the ladder from sliding out. The wall keeping the ladder from falling through the wall. If the ladder is stationary, what can we say about these 2 forces? Absolutely, they cancel out. So we can say that the net force in the x direction is 0. Those forces include the wall and the frictional force, which we describe as the coefficient of friction multiplied by the force, the normal force that the ground exerts upwards. So we can say that they're equal to each other. We can isolate for the coefficient of friction because that's what we're looking for. However, we don't have either of these forces. We have to figure them out to be able to find the coefficient of friction. So let's look in the vertical direction. We have in the blue line, that's Guy Fieri. I described that he's 6 meters up the 10-meter ladder, so he's a little past the halfway point. The ladder itself, anyone want to tell me how I chose the vector for the force of the ladder? The gravity acting on the ladder? Why is it in the middle? I heard somebody say it. It's the center of gravity. And the force, this would be the normal force, the force that the ground is exerting on the ladder, pushing it upwards, contributes to the frictional force. So we have those. And since the ladder is stationary, we can say also that the forces in the y direction are null, equal to 0. So the sum of these 3 forces we've identified cancel out. So we know, because I've declared, yeah. So we have that the force of the ground is equal to the force, Guy Fieri's weight, plus the weight of the ladder, which we compute 950 newtons. So now we have one of the variables we need to find the coefficient of friction. So we need to hunt for the other one, and to do that, we need to start looking at torque. We need to start looking at breaking up these vertical forces into their components. And we know that the ladder is not spinning about its fulcrum, therefore the torque must be 0. And so now we look at the components that constitute the torque, and there is the force that the wall is applying to the ladder, And that is negative because I've declared down positive. And it's multiplied by cos 30 degrees. And then we have, we're adding the rotational force caused by Guy Fieri's weight. We just multiply cos 60 degrees multiplied by his position up the ladder, 6 meters, and add the weight of the ladder itself multiplied by cos of 60 degrees multiplied by its distance, the center of gravity point, the halfway point, 5 meters. Now what we do is we punch these numbers in, and we have all these numbers. Thanks for coming, guys. So we have all these numbers. We have cos of 30 is computable in your calculator. We have the weight of Guy Fieri being 850 newtons, 100 newtons being the ladder. Everything else is just number crunching. So you come to 323.32 newtons for the force of the wall. Is everybody clear on how I got 30 degrees for the wall and not 60 like Guy in there? So if we use, this is going to be a throwback to, I got to close this. Throwback to grade 10 mathematics. What do you guys recognize here? So here's a perfectly horizontal line, perfectly horizontal line. These are parallel, and which means that any line that bisects parallel lines here, DPTZ, transverse parallel line theorem, remember that? This angle is the same as this angle. So this here is 60 degrees, which means that this is 60 degrees here. And we know that the perpendicular component of the wall force strikes a 90-degree angle with the ladder. And if we know that because this is 60 and TPTZ, this, trying to draw a Z there, a Z pattern, this angle is 60. And so you do 90 minus 60 gives you 30. This is a 30-degree angle. So now we have the two forces. The force of the ground is acting on the ladder and the force of the wall is acting on the ladder. So can we find our coefficient of friction? 0.34. Sounds about right. This is something realistically you could see on your exam. This would be a long answer question, right? Do you guys feel comfortable on these components, how we got to an answer in this question? Still a bit fuzzy? So there's an element of preparedness that you need for answering questions like this. If you were to never have encountered a question like this on your textbook and then walk into the exam, it would take you a few minutes just to understand how to answer the question, then a dozen more to actually punch it through your calculator. Right? So the point is to, a lot of questions get ripped out of your textbook and your online learning for your exam. So you'll encounter a lot of the styles of questions that you encounter in the exam ahead of time if you do some looking. A question like this, you have the advantage of already knowing where the forces are, what's acting on the ladder, and the steps you need to take because you've done the question before. And it requires a lot of thinking. When I came up with the question, it didn't take me a minute to do it. I had to think fast. So what you need to always remember is that if something is stationary, there is no net force. Net force is 0. And you can always begin by breaking things into components. So the first thing I did was break vertical forces into components. Then I broke horizontal forces into components. And what I needed to find was the force that the wall exerted on the ladder. And that's impossible to do without considering the torque. You will never be able to isolate for the force of the wall because you don't have the frictional force. And so to do that, I used the torque formula, and we were able to isolate for the force of the wall. My advice is to read through your textbook and cherry pick some questions that you think are really tough, and get to know sort of the theme of certain questions. Like this, I would call a ladder question, a torque ladder question. And there are tons of variations of it, right? I asked you to find the coefficient of friction. But suppose I gave it to you, would you be able to find the length of the ladder or where Guy Fieri was standing? So this is something that's new even to people that took physics in high school. So it can be a bit of a tough to wrap your mind around. You guys have my email and I'll give it to you again, but if you're going through questions and you need help answering them, you shoot me an email and I can write out on hand and show you how to do it. All right, let's head on to fluids. Density, that symbol is rho, not P, and it's defined by mass over volume. Careful not to confuse volume with velocity or speed. Capital V is always volume. Pressure, we described, capital P is equal to force over area. This is represented in newtons per meter squared. That is 1 Pascal, and the A refers to surface area. We also have the equation that we look at depth now. So the pressure at any added depth is equal to the pressure at depth 0 plus the density times gravity times the height above the initial point. And G is gravitational acceleration. Buoyancy, the easiest way to think of buoyancy and the most helpful, this should be your mantra. The buoyant force is equal to the weight of displaced fluid. And that'll make a bit more sense when we get into some actual questions. But the equation we have there is the density times the volume, which gives you the mass, times gravity. And we have this equation of continuity. And it's a mathematical way of describing things we've experienced millions and millions of times, and we've observed millions and millions of times. The density of a fluid multiplied by the area through which it travels, multiplied by its speed, is constant, no matter how you change the area there. And what that means is, suppose you had a big old hole in the bottom of a jug, and you were to slap some tape over the hole, and maybe a little tiny crack was left exposed. So now the aperture, the opening is much smaller. You'd have a much faster jet stream of water pouring out of that the bucket there. So fluids travel faster when the passageway is narrower. Leads us to Bernoulli's equation. Bernoulli dealt a lot with fluids, spent a lot of time with air. You might recognize Bernoulli from grade 3 science. We talked about planes and flight and low pressure zones. So Bernoulli's equation is described as the pressure at one area, atmospheric pressure plus the density times gravity times height plus 1/2 the density times the speed of the fluid squared. And then that is equal to the same equation at a different location. Let's get into some fluids questions. Suppose that a hollow cylindrical object is floating on the surface of water. This object has a mass of 300 grams and is floating such that 4 centimeters of its height is submerged under the surface of water, while 6 centimeters of its height is above the water. How many grams of mercury, which I'm representing as X, the gray, would need to be poured into the cylindrical object in order for it to sink? And I've given you the density of water there is 1 gram per centimeter cubed. And while we tackle this question, who wants to tell me the forces acting on the tube in the second diagram here? I'll give you a hint, there are two. Something's pulling it down, and something's pushing it back up. Exactly, they counteract. The buoyant force is what's keeping it afloat. Gravitational force pulling it down. And I'm asking you at what point, how much mercury do you need to add for it to sink? And what happens when something sinks? How does the equilibrium between buoyancy and gravity change when something sinks? The gravitational force exceeds the buoyant force. That'll cause it to sink. So the point at which it sinks is the point at which these two forces are exactly equal. That's when it's on the brink of sinking. So that's what you're going to be finding. So we can represent that as the buoyant force is equal to the mass times gravity. But we don't have the mass because we're trying to figure out how much mercury we need to add. So as far as this is concerned, it's a dead end. But we can represent these things in more variables. We can say buoyancy is the density of the water times the volume displaced and gravity. And that's equal to the total mass of the tube there, which is the mass of the tube plus the mass of the mercury that's added. That's multiplied by gravity. You'll notice some of these things cancel out. Gravity is no longer a factor. So we have the density times the volume is equal to sum of the masses. How do you calculate the volume that of water that the cylinder displaces? Absolutely. The area of the opening multiplied by the length of the tube. Cylindrical tube. And we can write that out. A being area, H being height. And that's a dead end, but we can write the same free body diagram on the left, buoyant force acting on gravity acting down. So we know that the buoyant force is equal to the density times the volume times gravity. We also know that the net force is zero because it's floating where it is, moving up or down. Therefore, we can say that the buoyant force and the force of gravity are equal. We can say that mass times gravity is equal to the density times the volume times gravity. So we can also say that the volume is equal to, as we said before, area times height. We don't know the area, but we know the height is 4 centimeters. We know that 4 centimeters is submerged in water originally. And so that gives us this equation where the density times the area times the height times gravity is equal to mass times gravity. Guess what cancels out? Gravity. And we can rearrange to find the area, which is the one variable we're missing from the equation on the right. And I told you the density of water is 1 gram per cubic centimeter. I told you it's the tube is 4 centimeters submerged. And I told you that the tube weighs 300 grams. So you can actually solve for A to get 75 squared centimeters. And that can happen. So the question was, what happens when the question is set up differently such that you actually need to use gravity to solve some of the variables? And at that point, you could pick either. You could put everything in kilograms, or you could put everything in grams, or you could put everything in meters, or you could put in cubic centimeters. The two things to consider are, one, what is your answer supposed to look like? Do they specify what units they want it in? What units seem most reasonable? The other thing to consider would be how much do I have to change my numbers here? If I want to put everything in kilograms, does that mean I change 6 numbers I already found versus putting one number into centimeters? So it's preference, whatever you find is easy. And so then we plug in that number, and this is going to let us solve for x here. If we rearrange, we get 450 grams, which means that if we look at scenario 1 and pour 450 grams of mercury into the tube, it'll be at the point where it's about to sink. Let's do another question about fluids. A beer keg with its top open to atmospheric pressure has a tap 80 centimeters from its top. The diameter of the opening is 2.5 centimeters. How quickly can you fill a 473 cubic centimeter glass? Assume that the keg is filled with Budweiser and that the density is equal to that of water. And I will give you Bernoulli's equation because you'll need it. Can anybody tell me what P1 and P2 are in this scenario? What is special about this question in regards to the pressure at these two locations? It's the same. They're both open to atmospheric pressure because the top has no lid and the tap has an opening. So they're both open to the atmosphere. And what that effectively does is eliminates, eliminates those from the equation, and you're just left with plugging in those numbers. Density of water, 1 gram per cubic centimeter, or 1,000 kilograms meter cubed, same thing. Gravity, 9.8 meters per second squared. I told you that the tap was 80 centimeters below the top. So I'm now assigning a height of 0.8 meters for the height of the top of the keg. And I'm saying that's equal to, you can say at the top, why have I only included rho GH and not 1/2 rho V squared at the top? Pardon me? There's no speed, yeah. So when fluid is leaving the tap at the bottom of the keg, you can assume that the beer level at the top of the keg is moving so negligibly that there is no speed. And on the right-hand side of the equation, we've assigned the tap a height of 0. So there is no rho GH component. We're just left with 1/2 rho V squared. And we're trying to isolate for V. And we get 3.96 meters per second. So we have the speed of the beer at the top. How do you get the flow rate? How much volume is leaving the tap per second? The volume flow rate is equal to the speed times the area. And I gave you the diameter of the opening. The equation for area of a circle is pi r squared. And to get the radius, you divide the diameter by 2, square it, multiply by pi. And we have V's 3.96. So you enter in all those numbers and you get 1,944 cubic centimeters per second. So how quickly can you fill that glass? Who wants to enter that in their calculator real quick? 0.24 is the right answer. It's quick. So that's enough of fluids. Let's talk thermodynamics. Thermodynamics is the last thing you guys covered, correct? Felt kind of rushed, right? Yeah. It's going to be rushed in your exam too. It's not going to be a major focus, but you'll need to know the basics, and here they are. Alpha is the coefficient of linear expansion, and it varies from substance to substance. It's not the same for copper as it is for iron, as it is for air, or some. So the linear expansion formula is given, the change in length experienced is equal to the alpha value multiplied by the original length multiplied by the change in temperature. That change in temperature is in degrees Celsius or Kelvin. Area expansion, denoted change in area, is equal to gamma multiplied by the original area multiplied by the change in temperature. Gamma is the coefficient of area expansion, and it's approximately equal to twice the alpha value. So if I told you that the alpha value of copper is 3, what's the gamma value of copper? 6, yeah. Volumetric expansion. Change in volume is equal to beta times the original volume multiplied by the change in temperature. Beta is approximately 3 times the alpha value for any given substance. And as I mentioned, T, temperature, is in degrees Celsius or Kelvin. Is, changes in magnitude between Celsius and Kelvin are the same. And alpha, gamma, and beta are expressed in 1 over degrees Celsius. So here's a question. A steel box, and I've given you the beta value for steel, is filled with water. There's the beta value for water. If both are heated from 25 to 100 degrees Celsius, how much water will overflow the steel box? You can assume that at 25 degrees, the box and the water both occupy 1 cubic meter. How are you going to go about answering this question? Will the steel in the water expand at the same rate? No. Looking at those coefficients, which is going to expand more? Any guesses? Yep. Water is going to expand more because there's a greater beta value. There's a greater change for difference in temperature. So how would you calculate the difference in expansion? One way to start is to look at the expansion of the steel and the expansion of the water. And you would take the difference between the two. So I'll let you tackle that. Let's work through this. Are these the numbers you entered in? Yep. 0.7 times 10 to the negative 3, also 2.7 liters. For water, you should have entered in the same numbers except substituting 75 times 10 to the negative 6 for your beta value. And that should give you 5.63 liters, or 5.63 times 10 to the negative 3 meters cubed. And I put up on the board that 1 liter is equal to 1 times 10 to the negative 3 meters cubed. So the overflow is the difference between the two. 5.63 minus 2.7 to 2.925 liters. How much water spills over? So that brings us to the end today. My goal today was to introduce you to questions maybe you haven't seen before that make you think a little differently. My advice to you would be to go home and when you study, look at the types of problems you see and how your prof might manipulate them to make them a little bit different, like that ladder question I was telling you about, even the normal course questions. My email is a resource to you. You can shoot me an email saying, hey, Mike, I don't understand this. Can you help me with this? I'll get back to you pretty quickly with a written explanation how to do it. And I'm always happy to Zoom with you guys if you want to work on something together. You can send me something ahead of time and I can look at it. You guys are going to be getting a copy of the presentation as well as the recording. You'll get a link to that through Zoom. And I will annotate the bugs we found in the presentation today. I'll go over them, and so you'll get another email later tonight once I've edited the video and the slides. And I can try to offer you a little bit of insight beyond physics. If you want to know what it's like doing a life sci degree, I did one. I did a 499 last year, and went pretty well. I started a master's. I'm in my first year. It's keeping me busy. So if you want to know what it's like, some do's and don'ts, I've developed study habits just through 5 years of schooling. The MCAT, I wrote that. I can give you some tips as well. One piece of wisdom I'd like to share about note taking. I saw this and cringed and cried in first year because a lot of people spend a lot of time coloring their notes or color coding or writing, rewriting, making them look nice. Organization is key, but you want to spend more time reading your notes than you do writing them. So a lot of people prefer to do stuff by hand. I like typing out my notes. Definitely read your textbook. A lot of people don't see the value in reading it, but it's literally where the exam questions come from for every class you ever take. So read your textbook, take very concise notes, and just enjoy the art of iteration, doing things multiple times. That accounts not just to studying, but also to writing. If you write an essay, the first one you write will be okay. And when you edit it and rewrite it, that'll be better. And when you do that a couple more times, it'll be great. That is also if you're in, I'm not sure what courses you're in, but if you need